Okay. As you can see, I need a mic, but Beatrice doesn't. I'm not nearly as vocal. Thank you, Beatrice. All right, so, okay. So what I was going to do was I was going to briefly talk about the reports that are coming up. Has everyone gotten, many of you should have gotten your data already, and you can begin working on your summation report. And the summation report, can people kind of stop talking? So the summation report, because a lot of people are asking me questions, I wanted to go over this, is posted as a Word document on bSpace under Resources, under Summation Reports, and you'll see it there as a Word document template. It's very similar to many of the questions you'll see at the end of Experiment 8. That means you're not going to turn in the questions at the end of Experiment 8, you're going to turn in the summation report, and it includes some other discussion questions that are not there, as well as one question, I think it's question 13 or something like that, that says summarize your data in 1 page or less. And that is asking you to summarize your data. That's part of your summary report. The entire report is not 1 page. Just that one aspect should be summarized at 1 page, double space, give or take, a third of a page, whatever. But try to keep it around 1 page, absolute max. And so that's your summary report. You'll turn that in to lab next time. Each person in the group writes their own report in their own words. Don't plagiarize your partner, okay? Don't divide it up and do all this. You can have this discussion among, you should have a discussion about how you might answer these questions, but answer them in your own words. Will be graded individually. They're individual effort reports. That's why I included 2 of these in this course so that the individuals will be allowed to shine. Okay, that is going to be the end of the plastic hydrolysis or bioplastics or plastics sort of recycling and hydrolysis and titration unit. And now we're going to start a unit on biofuels, and I wanted to do an outline of what the following weeks of this biofuel unit are going to look like. So, somehow my pencil is not very dark today. Okay, there we go. Week 1, we're going to basically do 2 things. We're going to set up a biofuel synthesis. This is next week. So you're going to set up a biodiesel synthesis. And you're also going to do a setup for testing ecotoxicity. So you're going to set up an ecotoxicity experiment, which basically means you're going to be growing radish seeds in different concentrations of various biofuels and organic solvents, and seeing how well the radish seeds grow under those different conditions, imagining, if you will, an environmental release of a particular biofuel or organic solvent. That's week 1 in a nutshell. Then, and by the way, at the end of week 3, there'll be another one of these summation reports, and you can see how this builds up. So by week 2, you're going to be getting your ecotoxicity results. Okay, and you'll be thinking about those, and you'll be performing a biodiesel purification. Because when you make biodiesel, you're going to have side products, glycerol, namely water, and you'll have excess hydroxide ion, sodium or potassium hydroxide rather, and yes. Sorry, perform. Sorry, my bad today. Perform biodiesel purification. And so you'll have to do a purification, because by week 3, you're going to burn your biodiesel. You're going to do biodiesel calorimetry. Wow. Biodiesel calorimetry. And so in that lab, you're basically going to try to figure out, the energy density of your fuel. Okay, or how many say joules of energy, kilojoules, probably in this case megajoules would be the right unit of energy per mole of biodiesel. And that will tell you about the energy density of that fuel. If you were to convert that to sort of say megajoules or joules per gram, then you would know, say, if I had a gas tank of this stuff, how many joules of work could I do? Some fuels have different energy densities than others, and so this is of course a key piece of the equation for thinking about transport fuels. All right, so week 1. So thinking about week 1, we'll think about ecotoxicity. And a key parameter that you'll be learning about is the LD50, and LD50 means lethal dose. And you could say 50% mortality, death. Probably simplest to say it like that. So we obviously don't like to say things like 50% death, so we like to say LD50 in the laboratory. And it's a useful parameter to know to understand how animal and plant species will respond to a chemical agent. Now, LD50 in the environment. Now, LD50 is not the only way to measure ecotoxicity, because chemical agents by themselves are not the only sources of perturbation for a particular ecosystem. There are many other perturbants, and I'll talk about this later. But there's chemical is one. Physical, you can imagine. Say removing trees from a forest is a physical change to the forest. Also, I guess you say killing the tree. Actually, it doesn't really kill the tree. The tree might grow back out of the rootstock. But in any case, that's more of a physical change to the environment. Maybe that's not the greatest example. You can say removing branches from trees or something like that. And then there's also other types of physical parameters, like heat evolution, say from a factory that produces a lot of waste heat. Say it's using water and it's feeding the water, taking the water in from one end of the river and then feeding hot water back into the other river. That's a form of thermal pollution. And of course, that's a physical perturbation of the environment. There's no chemistry being done there other than heating up the water, so we call it a physical perturbation. The other thing, of course, that can happen is, let's say your particular business makes, I don't know, some kind of waste product, but other kinds of bacteria or critters like rats or mice or something like that like to get into your trash and multiply. So you could be creating you could be affecting the ecosystem by releasing some biological agent in the environment as an effect of your industrial process by some mechanism. I mean, I'm not quite thinking of releasing mice, but maybe some kind of bacterial or fungal product builds up in your waste stream. So you need to think about all those different kinds of perturbants: chemical, biological, and physical. All right, so yeah, you'll think about LD50s ultimately as an easy to measure lab parameter, and typically the units on that are in units of, say, mass of, say, the toxin or the chemical agent. It might not be a real toxin, of course, if it's not very toxic. You might just call it a chemical agent, divided by the mass of the subject. Say if it's a rat, something like 800 grams. So you want to be able to standardize. You want to be able to standardize the units, because you might be testing a population of rats, and whether that population of rats is sensitive to toxin or not would depend not only on whether it's a male or a female rat. Let's assume we're controlling for that, but also the weight of the rat. Has anybody had experience with alcohol? Raise your hand. No, you shouldn't know. I'm just kidding. Okay, but as everyone well knows, it's well known. It's well known depending on your ethnicity, your race, depending on whether you're male or female, and then ultimately depending on your mass, you will be intoxicated differently, right? Same thing goes for many other toxins and poisons. We have to control for mass. So what we do to control for mass is we just divide by the mass of the subject in the population, and then by doing that, we control for that parameter, and we know how toxic it is per kilogram mass of subject. So that is a basic unit. So you can end up with something like this if your toxin is say microgram. Say microgram LD50 scale, you can have micrograms per kilogram of subject. This would be a good LD50 unit, let's say, for a reasonably toxic substance, actually. This would definitely be one that raises eyebrows. That's a very toxic substance. Not quite the most toxic substance on planet Earth, but I'm getting there. The most toxic substances on planet Earth are in the nanogram range. Yes? It means that if you, okay, so this is not one individual, because you can't die by 50%, right? So this is, say, for a population of, say, 10 or 100 rats. So what concentration would it take for a population of, say, 10 rats for 5 of them to die? So to do this experiment, you'd use quite a number of rats. What you would do is you take 10 rats and you expose them to different concentrations of toxin over a range of concentrations, and you say, what concentration of toxin will kill 50% of the rats? You don't want to know how much toxin it takes to kill all the rats, because you could kill them with 10 times the lethal dose or 100 times the lethal dose or 1,000, so it wouldn't tell you exactly where you're killing 50%. That's the point of sensitivity to the toxin, and that's what you want to know. If you go much higher than that, then if you look for the LD 100%, you'd be quite confused, because you couldn't distinguish the LD 100% from the LD 99% from the LD 98%. They would all look the same to you, and those could vary by orders of magnitude. Anyway, that's ecotoxicity and LD50 supposedly in a nutshell. I went a lot longer than I thought I'd go. So now we want to look at biodiesel synthesis. And we'll get back to ecotoxicity. So we need to think, before we get to whether biodiesel itself is toxic to the environment, we should probably make some first. So the chemistry is pretty straightforward. But first we'd like to see, let's see an example biodiesel molecule that's commonly made in the United States right now with our current agricultural inputs. This is methyl linoleate. 1, 2, 3, 4, 5, 6, down, up. Double bond. This is a lipid, okay, tail here. And people might not, this is a methyl group here, right? This is a methyl. And this part here is a fatty acid. This fatty acid happens to be called linoleic acid. Linoleic acid. And linoleic acid comes from soybean oil. Okay. And so overall, we call this compound methyl linoleate because this compound is, does anybody know what kind of functional group is prominently present in this molecule? Just blurt it out. Wait, say it more distinctly. Ester? Did I hear it? I don't know. I imagined it, maybe. Sorry. If I'm deluded, let me know. That is an ester. Okay. And so, technically, what you call this a methyl ester. And let's see. So how would you make this? Well, you start out with soybean oil, and you would add methanol. You're going to do this. You'd add methanol and a catalyst. This is a catalyst, potassium hydroxide. Methanol is methanol is going to be a reactant. Soybean oil is a reactant, and you're going to get some kind of reaction. And this reaction is going to be called transesterification. Transesterification. And as you might imagine, in that sort of reaction, we are going to do some kind of transfer of some group onto these ester bonds. So you might say, well, what's this transfer, the swapping, so to speak? Basically, we're doing a swap. And the swap is, the fact that soybean oil, each of the fatty acids, each of the linoleic acids are connected to glycerol. Glycerol has 3 alcohol groups on it, 3 alcohol functional groups. And I'll show you that in a minute. The linoleic acids are going to form 3 esters. When we add methanol and this potassium hydroxide as catalyst, then the methanol is going to swap for those glycerol positions, and then you'll release 3 biodiesel molecules and 1 glycerol. So you're going to have 3 biodiesels, 3 biodiesel molecules, 3 waters, and you're going to use 3 waters. Jeez. You're going to have 3 biodiesel molecules, 1 glycerol. And what I didn't mention is that there's one other reagent that's going to go in here, and that's going to be water. No, you're not going to use water in this thing. I'm really sorry. Don't worry about it. All right. Yes, the methanol is replacing the glycerol, and so you're going to end up with glycerol biodiesel. There's of course water. There's water in this reaction because the KOH is dissolved in water. To some extent, there's always a little bit of water with that. Although you should have made a methoxy product that you used. There's always a little bit of water lying around, but don't worry about it. It's sort of like a contaminant. All right. So, to understand this transesterification, you do need to back up a step and say, well, what is a fat and what is an oil? Okay, like soybean oil. And what soybean oil really is, soybean oil is made of triglycerides. Okay, and what a triglyceride means, as you might see here, this is glyc and this is tri here. So glyc means glycerol, and this is a glycerol structure. Very simple. 3 carbons, 1, 2, 3, 3 alcohol groups. 3 hydroxyls, alcohol functional groups. Okay, there's 3 of them there, and so we're basically going to join that with 3 linoleic acids. 1, 2, 3, 4, 5, 6, down, up, double bond, down, up, double bond. 3 linoleic acids, and then create. And unfortunately, it's hard for me to do that on one line because it's such a big fatty acid. Yeah. So this is your final product. There you go. So the name of this final product is tri-linolein. And this is a major triglyceride. Now, so as you might imagine, soybean oil is quite heterogeneous, but this is a dominant product in soybean oil. You can have various other lipids. Any fatty acid besides linoleic acid could form an oil by joining to glycerol, and so you can have various other combinations. Now, you might ask, well, why is this an oil at room temperature? And that's the double bonds create these sites of desaturation. These double bonds create kinks in these chains, and so it's hard for it to pack in making a solid fat at room temperature. And that's sort of an advantage of soybean oil on one hand for making biodiesel, because let's say you're in Minnesota where you grow a lot of soybeans, you'd like to use that in your trucks as diesel, but it's too cold to use pure biodiesel. You need special engine modifications to warm it up so it's not gelled under those extremely cold Canadian blast winter conditions. So that's a nice advantage of the desaturations. The disadvantage is desaturations create sites where reactive chemistry, polymerization chemistry can occur. Does anybody remember a mechanism involving double bonds that can cause polymerization? Do you remember that? What kind of polymerization reaction is that? It's like a nice review question, isn't it? Like styrene or vinyl? These kinds of reactions. What's that called? Addition. Polymerization, right? An addition, yes. So, on the other hand, you don't want to have gummy things going into your fuel injectors of your engine and gumming up the works. So soybean oil is not so good in that respect. But everything has its ups and downs, right? Okay, so let's think about some synthesis reactions. And like I said, the major type of mechanism is a trans-esterification. And so to review, we haven't really talked about this reaction, so I thought I'd do an example of something very simple. So this is ethyl acetate. Okay, so that's ethyl acetate. You can see on one end is an ethanol, and the other end is an acetic acid, or an acetate ion. This is isopropanol. And we'll do a trans-esterification, which is basically just as a fancy way of saying we're going to swap the alcohols. So, if I had a slight excess of, it depends on the chemistry here, but if I had a slight excess of isopropanol or an excess of isopropanol, I could really drive this reaction and form this product, this isopropyl acetate and ethanol. Okay? So that sounds great. I mean, that's good pencil and paper chemistry there. There are realities here. And the big reality, which is very important because as you hear in the business community, time is money. Time is important. And you really need to think about the kinetics, okay? The kinetics of the reaction. And we haven't talked a lot about kinetics, and I feel like I should at least say one thing since this is general chemistry. And you can think of kinetics as you have reactants on one hand, and these reactants are going to go to products. But to get there, you have to go over this energy barrier, which we mark with a double dagger symbol. This is an energy barrier. Double dagger. This is a double dagger here. Anyway, we mark what we call this the barrier with this double dagger symbol. Double dagger. And so, as you all know, maybe when you're coming to class, you got to go up this hill. Maybe I don't know. For people that live downhill. It takes more work. There's a little bit of activation energy to get the hill. And then eventually, at the end of the day, you go back downhill, you kind of feel. And at the end of the day, that sort of cycle of events, you hadn't really changed much in energy, of course, because you went back to where you started. But you have to admit that by going up the big hill, it sort of slowed you down. It sort of slowed down the process of you wanting to go up the hill and maybe completing the cycle. That's the same thing that happens in chemistry. You'll have some energy barrier, and that is going to impede the rate of reaction. So the bigger that barrier, the slower the reaction is going to go. So ideally, what we want to do as chemists is we want to lower the barrier. And the way you lower the barrier, as I've done here in red, is you add a catalyst. And I ran out of space there. You say add a catalyst, and then lowers the free energy barrier. Okay, so now adding a catalyst lowers the barrier and speeds up reaction. Speeds up the reaction. That is exactly what we're doing when we add KOH. So, KOH is a catalyst. And we would call this particular type of chemistry base catalyzed. Base catalyzed trans-esterification. Okay, so that's the idea. We want to speed up this reaction barrier. Wouldn't it be great if you could just, in the morning, lower the hill and come in, and then the hill stays down and you come back? Yeah, that'd be great. All right, can't do that. Don't tell anybody I taught you that. All right, so the base mechanism is going to look something like this. Now, I'm going to start to abbreviate this because you do not want to write out linoleic acid every time, right? So we're just going to abbreviate the linoleic acid like this. So this is basically a fatty acid. Looks with an R group. This is my linoleic acid abbreviation. Okay? So this is our trilinoline here, our triglyceride. And what we're going to do initially is we're going to take, KOH plus an ethanol. And what that's going to do is you'll have this hydroxyl group like this, and it has this nice extra pair of electrons that's ready to attack our methanol. And here's a methanol. So basically what's going to happen is something like this.